In part 4 of the Unit 5 notes, we will be looking into atomic radius and ionic radius. The size of an atom is defined by the edge of its orbital. However, orbital boundaries are fuzzy and vary under different conditions. In order to standardize the measurement of atomic radii, the distance between the nucleus of two identical atoms bonded together is measured. The atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded together, which you can see in the image below. Many properties of elements tend to change in a predictable way as you move down a group or across a period. This is known as a trend, and we'll be looking at a number of trends within this unit. The atomic radius trends are as follows. As you move from left to right across a period, the radius decreases, which you can see in both the graph and this picture right here. So lithium, which has 3 protons, is going to be significantly larger than neon, which has 10. So even though we have more matter, more mass as we go from left to right, the actual size of the atom or the radius is going to decrease. As you move down a group, the radius is going to increase. So we can see that as we go from hydrogen to lithium to sodium and so on, the atom is going to continuously get bigger. For our first checkpoint slide, we're going to have a couple of questions that we will be answering. For the first one, what causes the atomic radius to increase as you move down a group? This has to do with the number of shells. If you consider elements within the first column of the periodic table, hydrogen only has 1 shell for its valence electron. When we move down to lithium, it then has 2 shells, and that outermost shell is going to be further away from the nucleus, giving it a larger radius. As we go down again to sodium, that's going to have a 3rd shell, which makes it even larger. So as we go down a group, we are going to be increasing the number of shells, which increases the radius. For number 2, what causes the radius to decrease as you go left to right across a period? This explanation is a little more complicated because you are adding matter to the atom. So it would make sense if the atom were to get bigger, but it's in fact getting smaller, so there must be an explanation for that. The reason why the radius is decreasing as you go left to right is because you are adding more protons and electrons to the same shell. So remember that the shells are being filled up through the noble gases, and then once an additional electron is added, then a new shell would be added. But as long as you are filling into the same shell, you're adding protons and electrons which are attracted to each other. So as I go from left to right, I'm kind of adding additional attraction to the atom, and that is going to cause it to condense. For number 3, Ga and In both have a much larger radius than the elements before them. Why would this occur? Consider their electron configurations. I'm going to write out the noble gas configurations for each of these. So for gallium, the noble gas that comes before it is argon. And the configuration that would come after argon is 4s2, 3d10, and then 4p1. For In, we have Kr, which is krypton, and then after krypton, you would have a configuration of 5s2, 4d10, and 5p1. Now, if you consider what we were discussing in number 2, we know that as the atom goes left to right across a period, it is condensing, because we're adding electrons into the same energy level. If we expand upon that a little bit to consider it in terms of orbital notation, or in this case, electron configurations, 4s and 3d are very similar in energy to each other, very similar in distance from the nucleus. So as I'm filling in these electrons, the atom is getting smaller and smaller and smaller as it condenses. And then we add a 4p orbital, which is going to be further away from the center of the atom. That's going to cause a little jump in radius. It's not significantly larger. It's not like when you add a whole new energy level, a whole new, area, but it is going to be enough that you would see it within a graph. So why would this occur? You're adding a p orbital after the atom has condensed through the s and d orbitals. Right, and again, I know this is kind of condensed here. It should be s and d orbitals, not sand. All right, ionic radius. An ion occurs when an element has gained or lost one or more electrons. Cations have a positive charge because they have lost an electron. Anions have a negative charge because they have gained an electron. The charge of an ion is called the oxidation number or the oxidation state. When electrons are transferred, the radius of the ion will change compared to the size of the original atom. So that should make sense. We're changing the number of electrons, so the size of the atom should also change. You can determine the most likely oxidation number by looking at the group. So if we're looking at our elements in group 1, these all have one valence electron. Since they have one electron in that last shell, it's likely that they will want to give up that electron in order to become similar to a noble gas. So if you can consider the electron configuration of something like lithium, which would be 1s2 and then 2s1. If it were to lose that 2s1 electron to form a +1 charge, it would then be similar in size to helium. It would be a noble gas, it would be more stable. So elements in this first column are likely to want to lose one electron. That means +1. Elements in group 2 are 2 electrons away from being like a noble gas, so they would prefer to form a +2 charge. If I go across the periodic table into the p block, elements in this column right here, 3a, they could either lose 3 electrons to become like a noble gas, or they could gain 1, 2, 3, 4, 5 electrons to be like a noble gas. Between losing 3 or gaining 5, it's easier to lose 3, so they're most likely to form +3 charges. Once you get to the center part right here, carbon's group, which is 4a, they could go in either direction, because it's just as easy to lose 4 electrons as it is to gain 4. Once you get to nitrogen's family, 5a, at this point, we are more likely to want to gain electrons as opposed to losing them, because I would have to lose 5 or I could gain 3. So these would most likely be -3, -2, -1, and then by the time we get to the noble gases, these are already stable. So there's really no reason for them to form a charge. So they would prefer to have a 0 charge. Now for the transition metals which are here, many of these elements have multiple charges, and this is because of the d electrons that could participate in this bonding. For our next set of checkpoint questions, we are going to be trying to determine elements which will either be attracted to each other or not attracted to each other when they form ions. For the first one, we are trying to find one that will not be attracted to bromine. Now, in order to answer this type of question, you have to know the oxidation states. Bromine is in group 17 or 7a. It's going to form a -1 charge. Calcium is in group 2. It is likely to form a +2. Iron is a transition metal. Because it's a metal, it's likely to form a positive charge. We don't know the exact charge that it will form. It could be a +2 or maybe a +3, but for our purposes for right here, we just need to know it's going to be positive. Sulfur is in group 16 or 6a. That's going to form a -2 charge. And lithium is going to form a +1 charge. It's in group 1. Now we want a an element which will not be attracted to the bromine. That means that they should be the same type of charge. They should both be negative. So the best answer here would be sulfur. In our second question, we are trying to find elements that would be attracted to oxygen. And our oxygen would form a -2. So since oxygen is negative, we want to try to find something that will be positive. Chlorine's oxidation will be -1. Nitrogen, -3. Iodine, -1. And sodium, +1. And I'm just getting these charges directly from what I was talking about on this picture right here. So based on the group numbers that they are in. So since sodium is a positive and this is a negative, sodium would most likely be attracted to that ion. In this checkpoint question, we are trying to draw Bohr models for lithium and lithium +1. So we're seeing how it is going to change when it becomes an ion. Now for the lithium, the protons are going to be 3 based on the atomic number, and neutrons are 4. We have 2 electrons in the first shell and 1 electron in the second. Now when this becomes an ion, we know it's going to form a +1 charge. What does that actually mean? The nucleus is going to remain unchanged. We don't add or subtract protons. That would change the identity of the atom. And we're not going to change the number of neutrons either. So the nucleus is going to be identical whether we are talking about regular lithium or lithium +1. What's going to change is the number of electrons. If I have a +1 charge, that means I must have lost one of the negative charges. So my Bohr model would now look like this. Now for the follow-up question, it says, how do you think the radius of the positive ion is going to compare to the radius of the original element? And this one is relatively simple to see. In the process of going from lithium to lithium +1, I have lost that outermost shell. So the radius is going to decrease. Part of that is because we lost the shell. But there is a secondary reason for this. If I consider this in terms of a tug of war, when I had this situation, I had 3 positives versus 3 negatives. So if we're playing a tug of war, the flag would be right in the middle. But here, we have 3 positives and only 2 negatives. The nucleus has a greater relative pull compared to the electrons outside. So this shell, even though it's still the same 2 shell that I have in this drawing, it would actually be pulled in slightly. So not only did this get smaller because of the loss of the outermost shell, the shell that remains is going to be pulled in a little bit more closely than where it was before. So the outer shell is pulled in more closely. In this checkpoint question, we're doing the same thing except now with a negative ion. So first for chlorine, we are going to have 17 protons and 18 neutrons. For our shells, we have 2 in the first, 8 in the second, and 7 in the third. Now when this becomes chlorine -1, our nucleus is going to remain exactly the same, but our shells are now going to be 2, 8, and 8. The -1 charge means that we have picked up an extra electron, and that electron is going to fill into the final shell since there was still space. Now let's think about how the radius is changing here. This one is not quite as obvious as with the positive ion. I did not gain or lose any shells. But if I think of it in terms of that tug of war again, I have 17 positives versus 17 negatives in the original atom. In the negative ion, you have 17 positives in the center versus 18 negatives, which are in the shells pulling outwards. So even though the shells are in the same exact places that they were before, each one of these shells is going to be a little bit further away than where it was before, because the nucleus cannot hold on to the 18 electrons as well as it could have held on to the 17 electrons. Based on that, we can say that the size of the radius is going to increase. And for our explanation, we could say that there are more electrons compared to protons, or that there is a greater relative pull going away from the nucleus. In summary, when electrons are lost, the radius will decrease. This is due to the loss of a shell and the increase in relative pull from the positive nucleus compared to the negative electrons. There are more protons than electrons. When electrons are gained, the radius will increase. This is due to the increase in relative pull from the negative electrons compared to the more positive nucleus. There are more electrons than protons. That concludes Unit 5 Notes Video Part 4. When we come back for Part 5, we will be looking into ionization energy, electronegativity, and electron affinity.